In problem 20, we're asked to solve each inequality and then draw a number line graph to represent the solution set. In problem A, all that I really need to do is multiply both sides by -5/3, the reciprocal of the number that's there. But what's important to remember is that when we multiply an inequality by a negative or divide by a negative, we need to reverse the inequality. So this gives me x is greater than or equal to -100, 5 times 20, over 42. Of course, 100 and 42 are both even, so I can divide each of those by 2 to get -50 over 21. So my solution is x is greater than or equal to -50 over 21. And then to create a number line graph for this solution, let me draw a line. I'll plot 0 just for reference there. Let me also add -50 over 21. And then to graph my solution set, I want to include that number. So I'm going to put a solid dot there and then shade the values above it, because I want the solution set to be values that are above -50 over 21. Another version, if you prefer, for a graph like this, we could plot -50 over 21, maybe add 0 there for reference, create a solid dot, and then a line above that points to the right. Part B is a little more complicated because we have an absolute value inequality. So let me treat this problem in a different way. I'm going to start by solving the related equation. I can simplify this equation into two parts, x minus 5 equals 8, and x minus 5 equals -8. Because if that expression in the absolute value is -8, the absolute value will turn it into +8, and so this simpler equation would give me that solution. Of course, the two solutions that come from these equations, if I add 5 to both sides, I get x equals 13. In the second equation, I get x equals -3. So I'm going to think of these two numbers, 13 and -3, as boundary values to my solution. These are the values that make the statement equal, and I want to figure out where the inequality is. So I can use a number line graph to figure this out. -3 and 13 are the two boundary points. They divide the number line into 3 regions, and the question is, which of those regions do I want to include as a solution to the inequality? One way to think through this is to test each of those regions. I could see, is the statement true when x equals -5 as a representative to that leftmost region, or x equals 0 as a representative to the middle region, or x equals 15 as a representative to the upper rightmost region? Well, if I plug in -5 for x, I get -10. The absolute value turns that into +10, and 10 is not less than 8. So that region doesn't satisfy the inequality. If I let x equal 0, I get the absolute value of -5, which is 5, and 5 is less than 8, so that does satisfy the inequality. And if x equals 15, again I get 10 is less than 8, which of course is ridiculous, so that doesn't work either. So my solution set are the values in between -3 and 13. Since it's a strict inequality, I don't want to actually include -3 or 13, so I can put open dots at those endpoints to show that they're not included in the solution. Finally, let me write the solution set as a compound inequality. -3 is less than x is less than 13. So to summarize our results here, in the first inequality, we saw that x has to be greater than or equal to -50 over 21. We had to be sure to reverse the direction of the inequality when we multiplied by that negative number. And we graphed our solution set in two different ways here. In part B, we took a slightly different approach. Using the related equation, we found boundary values of 13 and -3, and then determined that the x values between those boundaries satisfy the inequality by testing points from each of the three regions created by those boundary points, -3 and 13.